Engineers, here's a quick warning. If you're still trusting a single full-cycle decline fit or a best fit B-factor trend, you may be walking straight into one of the most common and costly mistakes in unconventional analysis. Watch how Thad Toups explains why this approach consistently overpredicts EUR and what real engineering should look like.
How many times have you seen this in a data room? It's a best fit B factor, right? Again, but we still see folks relying upon a best fit B factor like this. Plenty of literature out there that goes into why that's not appropriate, but if you're going to model a best fit B factor, you're always going to be overestimating reserves because that B factor comes down over the well's life. So the better way to do that is to fit the near-term production with a lower B factor that's more aligned with the flow regime that well is in. So we usually say consider flow regimes or consider writing down your reserves later. In this cartoon here, it doesn't look like much, but the change in B factors associated with fitting the more near-term production is actually a reduction of the EUR of this well by about 20%.
Now here's the part engineers miss. When you rely on a single segment full cycle decline, you're not just slightly wrong, you can materially distort reserves. Using that shortcut can push your EUR as much as 25% higher or even more. Here's Thad with the evidence.
We've done several case studies on that subject where we'll take a best fit B factor on a group of wells. I believe this was 300 or 400 wells in the Bone Spring of New Mexico, and best fit B factor EURs versus a multi-segment B factor or a B factor more fit for the flow regime of the well. And we often see that a best fit B factor can be up to 25% too high on the ultimate recovery of that well.
And here's the real engineering step that full-cycle shortcuts completely miss. Flow regime identification. Whether you use RTA, material balance time diagnostics, or vintage-specific B factors, the objective is the same. Understand where the well actually is in its life, not where a curve fit guesses it should be.
So how do you diagnose what flow regime you're in? Material balance time plots and there's dozens of ways to identify this. Some folks use the gas-oil ratio, but you can look at when you start to deviate off of your inverse of the rate versus square root of your material balance time. When you begin to deviate off of this initial slope, that's the end of linear flow, right? Another way to look at it over here on the top right is your rate, a log rate versus log material balance time. Again, you've got a half slope here during the linear portion where I've got the blue wells highlighted, or the blue monthly production highlighted here. And then once you get to a full unit slope, which is down here on this part of the curve, that's when you're in fully boundary dominated flow. So anything in between a half slope and a boundary dominated slope, a unit slope here, is in a transitional phase.
This is exactly why modern reserves work demands tools that go beyond simple curve fits. PHDwin V3 handles multi-segment declines, boundary-dominated flow, and full flow regime diagnostics, all in one engineering-grade workflow. If you want short, practical breakdowns like this, subscribe and follow along as we show you how to build reserves and economics you can rely on.